We did things the hard way in this first session. Come back from lunch. We do things in still the hard way, bear with me, but hard in a little different way. Right? Now we're talking about the actual parallel programming with MPI-IO. You might go and use MPI-IO directly. It might be the right fit for your application. There are probably some other approaches you could take to do your I/O efficiently, but if you do, you should at least know what's going on in the MPI-IO approach and try to do at least that much, if not more. Because when we think about parallel I/O in an MPI context, it may seem a little strange to think about message passing and files. But if you think about sending a message is kind of like writing to a file, kind of. And the same things that made MPI useful, communicators and data types, those can be used in an I/O context to provide some more information about what's going on in the I/O process. So as was pretty clear from the example, sending everything back to rank 0 is a big headache. Rank 0 can sometimes run out of memory if there's enough processes. It's a bottleneck to the I/O. There are very few, if any, cases where you really do want to send everything to rank 0 and have it do the write. You may want to have rank 0 do a read of a small data and broadcast that. That might make more sense. But in a case where everything's funneling down to rank 0, of course, that looks like a non-serial, a non-scalable approach. So we're going to talk a little bit about what's going on inside the MPI-IO library. We'll talk a little about MPI-IO routines. And I'm demonstrating all this stuff because it's a foundation for what's going to happen in parallel netcdf and HDF5. And so even if you don't use MPI-IO directly, hopefully by knowing what's going on, you will be able to understand a little bit about the behavior that these higher level libraries give you. So again, talking again about collective I/O and what that means. And the big benefit of collective I/O is that we can turn what might look like a bunch of small requests, maybe non-contiguous, maybe contiguous, but many small requests, and we can transform them in whatever way makes sense to large collective accesses. And today, I should probably rephrase that, into whatever access makes sense for the file system. Now, for many years, that was a large collective access, but in the world of burst buffers and SSDs and NVRAM, maybe that's changing a little bit. I think for the most part, reducing the number of system calls is always going to be helpful, but something's going to happen inside the MPI-IO library to make your I/O do better. If I were to show a simple example of MPI-IO, and you can contrast this with the simple POSIX example from before lunch, opening a file is not so different from a POSIX system call open, but now we take a communicator. This communicator, like all MPI communicators, indicates who's working on the process. It isolates their communication patterns from everybody else outside of the communicator. We set a file view. This is annoying for MPI-IO, honestly, but the decoupling of what's going on in the file and what's going on in memory is an artifact from some design choices made with the MPI standard. And the thought was that you'd set a file view and reuse it over and over again. In practice, nobody does that. They set the file view every time. We should have written an MPI standard that says that the write would describe both the memory and the file layout, but right now that's decoupled. So we describe how is data laid out in the file. In this case, it's scattered through the file in some pattern. And then MPI file write all. It looks like any other collective call. You have a buff count data type tuple, and this describes the memory. And now your scientific data structure is described with the MPI file write call. The file view describes how you wanted it on the disk. And the two work together to give you an efficient access. The underscore all makes it explicit if these are independent or collective routines. There are probably only a few routines you need to actually do some MPI-IO, but we can talk more about all the different aspects of it. For the sake of these examples, write all and read at all should be enough. Another thing to point out is in a collective call, everybody is specifying locally what's going to happen. Some processes may not even communicate at all. They may contribute 0 data to the operation. They still need to call it. A collective routine means everybody has to call it, or you'll get weird hangs. The library might be doing something where that process is involved in the I/O in some way. All right. So it's hands-on time. I hope your shells haven't timed you out. I hope you have your logins ready to go. We're going to start with that I/O from master example, that exercise 3. And we're going to make it parallel now. So there will no longer be I/O from master. Everybody's going to write one of these rows to the file. So remember, we're also storing a small header to describe what's going to happen. So we need to skip that header. Well, the MPI file set view call, in addition to describing what's in the file, and in this case it's pretty simple, it's just integers, can also, with the second parameter, skip over any extra information. Typically that's a header. In this case, the 3 integers describing the experiment. And then everybody writes their one slice. So with write at all, the at part is explicit offsets. So rank 0 is going to write the first row, rank 1 the second row, so on and so forth. And how much data are we going to write? Well, again, the buffer count data type tuple is the values array and xdim by ydim. And what kind of integers, what kind of values are they in the array? It's MPI-INs. Oh, yeah.
Can you just explain a little bit more verbosely what's going on? What is a view in this context?
If you don't set a file view, the default file view, or what's going to happen to the file is it's going to be a linear stream of bytes from offset 0 to offset 1000. And if I write some data to it, I'm just going to go 1, 2, 3, 4, 5 through the file. Now that might be what you want. And in this case, that's what we're doing. We're writing out linear rows. But if we were going to write out a column of data instead of a row, and when we do the read example, we'll see this more. We need to be a little more sophisticated in how we are, what bytes we're seeing on the disk. And so if you were to, so a couple examples. Perhaps you have a particle-oriented simulation. You are globally tracing 2 billion particles, but you process 10 have particle 10, 35, and 2000. Those particles would go somewhere else in the file. Now, with the file view, you would say, okay, here is the part of the file that I'm going to write to. I'm going to store these pieces. There's a little bit more to file views, but for the sake of this example, I can leave it on later. But it's a way of describing the structure of data as it lives in the file. Whereas MPI data types in this MPI file write all example describe how data is structured in memory. It's the file view that tells you how data is structured in the file. In parallel netcdf, to talk in the future, in parallel netcdf, the file view will be how we turn multidimensional arrays into writes to the file. And a lot of the details will be hidden by the library. That is a really big topic. When I was first learning MPI-IO, I tripped me up a lot too. So I'm happy to talk more about that if it's still unclear.
So we're basically setting like a stride so that each process writes with some stride in it.
Yeah, that would be one way of thinking about it. And if you were to write columns out of an array, each process would define a separate. They all have the same stride, but they would be slightly offset from each other, so they would be not writing to the same places, and that's how you convey that. So in this case, if you so the view for the purple process would be to say block 0, 2, 3, 4, 5, 6, 8. Yeah, okay. So block 0, 4, 8, 12. You could just describe that with a list of some kind of index type. And then the orange process would describe a separate list of I/O of regions to write to, the 3rd, the 7th, the 9th, and so on. So then because they're describing distinct file views, they are that's a legal operation. We can't have overlapping file views in MPI-IO. The writes have to be non-overlapping, and they have to be increasing in the file. And other aspects I want to talk about here. But by doing this file view, then you don't have the problem of rank 0 stepping on rank 1's data. They all have distinct views of the data, and it won't do that.
There is no need of any kind of barrier in this kind of exercise, right?
That's right. The barriers, or the barrier would be sort of implied in this example. File set view, it takes an MPI file handle, It is a collective call. Is it collective? Yeah, I think it is collective. Yeah, that was one of the headaches, because set view is collective. It's a collective call, everyone calls it, but so there's some implicit synchronization with set view and file write at all. But you could absolutely have the case where process 0 is hitting the I/O part minutes before process 10 or 50. Now will very likely and quickly come to a part where if the processes are imbalanced, they'll spend more time in I/O. It will look like more time in I/O. This is an interesting but kind of a off in the weeds topic. If a process spends a long time in MPI file write at all, is it spending a long time because it's writing a lot of data, or is it spending a lot of time because it's waiting for other processes to contribute their share to this collective? The answer is not immediate. It's not immediately clear from timing MPI file write at all, and to get that answer requires digging into the implementation, pretty deep into the implementation. So that's another thing to be careful of to be mindful of when you're timing these things. It's very easy to get a result, and Darshan does this too, where Darshan will tell you, you spend a lot of time in these I/O routines, but the distinguishing between I/O, as in writing I out to disk, and what we call pseudo-synchronization, waiting for every process to hit this collective, that's a subtle bit of timing that's harder to measure. Putting a barrier in front can reduce that pseudo-synchronization cost. So you might see that in some benchmarks. But in practice, if you're calling collectives, if you're calling a collective I/O routine, the implication is that your processes are already fairly well balanced work-wise and will hit that at about the same time. So let's talk a little bit about the examples, about how you work this out. Again, there's a solutions directory with all these solutions solved out, and so if you're still working on some of this stuff, you can see how I did it. I think I gave the file view in the examples, but I don't remember anymore. We can mix independent and collective I/O on the same file handle. Once you open the file, you are not restricted to one or the other. You can go back and forth as long as you're careful not to step on anybody's toes. But in this case, rank 0 is going to just write out the header. And then that's going to look a lot like the POSIX write. There's a small number of bytes in that header. And then collectively, everybody will write out the data. We're all, so here, the rank times xdim times ydim. Because we set a file view saying our view is integers, instead of, here's the work here. Because the E type and F type, the file type of the file, are integers, not bytes, we can count in the file in terms of integers, which is a little more natural in this case because we're dealing with an array of integers. You'll notice there's no call to size of in here. Now there is a call to size of in the file write call because we're saying how much data we're writing. That's a memory description. So if you are able to run that example, you'll have a Darshan report. Well, let's talk about this. Let's reason out a little bit. We made one call to independent writes, and we made one collective call from probably about 32 processes. One node of theta. The way we've set up our app run is going to be 32 MPI processes. How many? So that's 32 MPI-IO calls. How many system calls do you think that's going to turn into? Do you think it's going to be 32? Yeah? Yeah? Well, it's actually going to be 1 because all the processes funnel down to one process who's the I/O aggregator, and that does the I/O. And so that's kind of an optimization happening inside the MPI-IO library. So even though we're doing many calls and they're all contiguous calls, it still ends up being more efficient to have one process do all that. And that's a decision, a tuning decision that the library makes for you. You don't have to worry about getting that right in the application. Yay.
But you still see speed up?
Still see a speed up. Well, for these small applications, the notion of speeding up is kind of a challenge. But let's talk about a larger workload. If you're issuing many requests to the file system, it may be the case that you may want to issue them as fast as possible and let the file system deal with many requests. But on most of these file systems, they're not going to be very happy with essentially a denial of service attack. So using these library coalescing and transformation techniques, we turn on the order of 10,000 operations At large scale, it'll be hundreds of thousands of operations. We turn them into a smaller number, maybe 1,000 or 100 operations. And so, yeah, you will see a performance difference. We'll talk a little bit about the tuning knobs. There are a lot of tuning knobs you can set. And so the usual answer in high-performance computing is it depends. So yeah, you might see bad performance from this. And there probably are workloads where having a small number of I/O aggregators gives you worse performance. Unfortunately, when we get to that point, you're using MPI-IO and you're seeing weird performance, that's when it's, talk to one of the site consultants or someone like me, and we can work about what the right value there is. We'll talk a little more about default tuning parameters and how to adjust them in a little bit.
So the appeal of this then is that you don't have to, for yourself, send in everything to one processor.
Right, the library might end up doing that for you, or if it detects that the I/O is small and well-formed, or because these small examples are running on just one node, it might make sense for one node to do the I/O instead of everyone fighting for I/O bandwidth and network bandwidth. If we were to use a whole rack of theta, we'd probably see 40-some I/O aggregators. I don't remember the exact numbers of machines and how the aggregator placement, but that's one of those implementation details that we can sort of count on. We can hope that the vendor gets right, or file bug reports if they don't. So what am I going to say here? Right. So okay, if you want to answer your question, is it better to do many small requests or let the I/O aggregation happen? And you could turn this write at all call, just drop the all and do MPI file write at and see what happens. You could time both of those, and maybe because your workload is imbalanced or because the tuning is weird, maybe you get better performance. It's a lot easier to go from a collective routine to independent than it is to try to add collectiveness back later, because everybody has to reach the collective point in order to make progress. There can be cases where if you want to add that synchronization in, it can be a little bit of a challenge. Whereas if you always had it, relaxing it after the fact is pretty easy. Okay, don't have Darshan reports. We'll call it later. So let's talk a little bit more about what's going on with the collective aggregation. There are a couple things that can happen in these transformations. We talked a bit about turning small requests into large requests. Another thing that happens a lot in these file systems is because they are designed as general purpose file systems, there is very little way to tell a file system, hey, I'm going to do this workload, just get out of my way and do this. Now there's direct I/O, but that's really meant for database type workloads, and that turns off all the caching. When you're dealing with a parallel file system, they're going to break up the file into locks. Now no file system implements byte granularity locks. That's an expense that's too high to pay right now. So usually it's 4K or 4 megabytes or something like that. And each one of these lock boundaries in the file is a point where there's an implicit lock that a client gets, so they can modify that region. There are F-control locks where you can get explicit locks as an application, but that's not what I'm talking about. I'm talking about operating system level implicit locking done to make sure that no two processes step on the same block. This is an artifact of the POSIX consistency semantics, which say if two processes write to the same region, the last writer has to win. And so we have to know who's going to write when and coordinate that. But this locking is a challenge when it comes to consistent access, because if you are nicely aligned to these locks, you might get pretty good performance. But if you're just slightly out of skew, so if you look at the green and the orange, they are not exactly lock aligned. Maybe they were working on something that's more natural to their application, hundreds of bytes instead of power of 2 bytes. Now a write to the overlapping region requires two processes to fight for a lock. One process is going to win. The other process will sit and wait, and then when the first process finishes, the second process will come in and get that data. And that will be a big performance hit. Now that happens sometimes from a header might shift people's work or otherwise. Yeah, and another way is if you're accessing data in an array slightly differently, maybe you're doing block accessed instead of row accessed. Now there's many chances to do these lock contentions. And the more of these happen, the slower the performance is going to be. So you'll often see that, that writing, even though there's many layers of caching involved, can have some places, some performance pitfalls that the MPI-IO library can help smooth out for you. So when we do a collective I/O, right, in this case we have process 0, 1, and 2, and they're all writing some kind of structured data out to a file foo. We're going to transform that data a little bit. We're going to do some work under the hood that you don't see, so that we get a better, more file system friendly layout. Another thing that might happen in the MPI-IO library is something called data sieving. If the goal is to reduce the number of operations, then we can do a read, modify, write. And this is a technique you see throughout the software storage, the storage stack. Read a block of data, make modifications to a subset of the data, and then write that modified block out. This read, modify, write step we call data sieving in Romeo. So we could imagine a process that wants to write a non-contiguous thing out, pieces of an array. We'll read in a block, we'll make some changes in step 2, and then step 3, write it out. But this 3-step process requires some modification, some serialization. We don't want anybody to come in and modify that block while we're modifying the block, or else you get some problems with corrupted data. So it's weird, right? We're reading in more data than we wrote. Where's the trade-off? Well, obviously, if you're modifying just 1 byte and you're reading in 4 megabytes, maybe that's too extreme. On the other hand, if you're able to keep 90% of the data, if you're modifying 90% of the data, that's probably right. Knowing what the trade-off is for collective data sieving is one of those tuning parameters that would be like an advanced talk. We talk about more how you would evaluate that and tune that through hints and environment variables.
I don't know very well, I don't understand very well what you mean by false sharing.
Okay, the question is, what does false sharing mean is the question. And false sharing is this technique where both blocks end up working on the same data, but they don't know it. And this is what I'm talking about when you have the potential for corrupting a data block. If you are not serializing access to these regions, you'll get a case where the orange and green process will read an entire lock region, make a change, and write it out. Who's going to win in that case? So you'll get maybe if you're lucky, you'll get half a block of reasonable data, or maybe you'll get completely scrambled data depending on how the file system handles that case. So that's why we have to worry about coordination and serialization. The false sharing problem is when two processes want to modify different parts of the data that end up being in the same lock domain. So there is a
there you have an inconvenient configuration of views, so to say, because you have the final of a view of a file in the middle of a block.
So yeah, right. It's inconvenient because the processes are not nicely aligned to the block boundary. Now that's an artifact of the system hardware that we would hope application scientists wouldn't need to worry about. This is a perfect example of something that the MPI-IO library could manage for you, and through the collective algorithm, make sure writes end up in the right place without you worrying about that as an application writer. So a good example of how these hints and tuning parameters and these transformations happen shows up in an I/O benchmark we were using called the S3D turbulent combustion code. It's modeling a jet engine and how it consumes fuel, and you want that to be efficient, right? You want to have the most fuel turned to the most thrust or something. I'm not a combustion person, but the reason why I know this code is because they write out to some multidimensional arrays. And as we talked about writing out these arrays should be pretty straightforward, but when I was running this on one machine, I was using a configuration from a different machine, and all the tuning parameters had been disabled. And so I had to have a really small job to get it to run in any reasonable amount of time, and even so, it was still 30 minutes, 1,400 seconds, because all of the data sieving and two-phase buffering, collective buffering was turned off. So in this application, they're writing out several multidimensional arrays. I think it's 4, and I think it was 4 arrays. And that turned out to be 64 MPI-IO operations, which, because everything was turned off, turned into 100,000 POSIX operations. This machine is pretty old, but even on a modern machine, 100,000 would be pretty slow. Most of these file systems respond better to fewer, larger requests, as we've been saying. So even though I was only writing out 6 megabytes, it took half an hour. I don't even know what the number is. It's a ridiculously slow gigabytes per second number, probably bytes per second number, right? So we turn on data sieving, and now the time drops by 1,000. It only takes 5 seconds to do data sieving. Now, we are writing out 80 megabytes instead of a smaller amount of data, but that's because these were arrays, and there's some of this data sieving going on. So we go one more step with the two-phase collective buffering, and now there's only 5 POSIX operations. One's for the parallel netcdf header, which we'll talk about, and then one for each of the variables. There is only a small amount of I/O time, half a second, and so these tuning parameters really do make a big difference. Today, what we would hope is that each vendor would have the right set of tuning parameters. The reality is that you have to do a little bit of work on your own sometimes. Oh, and all this data came from Darshan. We were learning this from the Darshan output, so we could see exactly how many operations were happening, and we could understand pretty clearly why this was the case. So let's take a little time and try to read out of our examples, right? We have now notionally a 2D array. We've written out by row. We want to read back differently. You could imagine if you read back the same way you wrote, you won't catch any problems in your file system or in your algorithm. But by reading back a little differently, you know for sure what's in the files. It matches what your mental model of the file is. So in this case, we're going to use a subarray. I'm going to ask you to try to quickly create an MPI data type. The subarray data type will describe both the overall array and then the subset, the one row we want to read. Everybody can read the same thing. There's a lot, reading is a lot less restrictive than writing because it doesn't matter if everybody reads the same data. That's fine. There's no one's changing bytes. And we can do a collective read all. And so let's see if I gave you enough to work with in the hands-on example. When I did this the first time, I got the order wrong. I got some segfaults. So I've been doing this for quite a number of years, and I still got it wrong the first time. I'm not embarrassed to admit it. Describing the array with subsets, right? There's the idea of a global array, a logically global array in the file. So when we talk about subarray, we're going to know the overall array. That's the sizes array. There's going to be a subset, which is going to be, as we talked about, each process is reading how much data? It's going to read. Each process is going to be one row. Each row is nprox high. And where's it going to start? It's going to start at the very first row of the array, and it's going to go until it reads the whole array. So once we have this subarray type, we set the file view. Once again, we're skipping over that small header, and then we use a subarray data type. Now, with the file set like that, we don't have to worry about offsetting the file. We'll just read the file. We can read from the file handle. We can read nprox int into the read buffer. So you can see the fully worked example inside the subdirectory. Because we're having problems with the queue, let me look at let me show you the Darshan output for that. I ran this with 32 processes, and so you can see, if you look carefully in this first chart here, in the I/O operations counts, the blue bar is how many MPI-IO calls were made. 32 processes made an MPI-IO call. That turns into a small number. It looks like 2 read calls. So you can see where that gets consolidated down to a small number of processes. We have 64 processes opening, 32 in the write, 32 in the read. There were more POSIX calls. What's going on there? Well, that's a reflection of a small optimization done inside MPI-IO. On GPFS, if everybody creates a file, there is a contention because every process is going to fight for a lock on the directory. And then whoever wins that will create the file. And then everybody else will try to create it again. It ends up being pretty expensive. But because this is MPI, we can do some optimizations on behalf of the user. We can have one process create the file, close the file, and then everybody else opens the file just regularly. And opening the file regularly is a fine operation in GPFS. So yeah, it's an extra system call, but it in some situations helps take a faster path in the file system. Again, I wouldn't want an application person to worry about, well, I'm on GPFS, I better do this. I'm on Lustre, I better do this. We can tuck that away inside the MPI-IO library. But that's why you see these things happening in the Darshan output. Other things to look at here, there was small header I/O and small writes. We talked a little bit about surprising tuning parameters. I like this example because I often will tell people, as I've said many times today, please use a single shared file. Your life will be a lot easier and happier that way. And so people go and they try that. And when they use a single shared file, their write performance goes in the toilet. And they look, what did I do? I just steered everybody into a very sad state. Well, and then they'll use one file per process because you're a computational scientist. You want to get things done. You want to get an answer. I don't care about the problem, the long-term implications. I want to do one file per process and move on. And they get really good performance that way. Well, what if instead of using a POSIX shared file, I used MPI and wrote to a single shared file? Well, we're out of the toilet, but we're not really doing really well anyway. It's still a third of the performance of what a file per process was getting. And the reason why is because this was on Mira. This was on Mira. But the tuning parameters were set 2 machines prior. And as we talked about aggregators. We talked about, should you have 1 process or 10 processes writing the file? Well, they were having a very small number of processes writing to the file. And they weren't able to light up enough I/O storage links to get good performance. But we reported to IBM, hey, look, if you change this default a little bit higher, you're going to get better performance in more situations. They did that, and in the tune column, everything's happy again. You get better performance you get better performance than the file per process approach, and you have a single file to work with. Everyone's happy. It all works out. I just want to give this example as you might on newer machines, and every machine really is new, right? They only last a few years. It takes time to get the nuts and the kinks worked out of all the tuning parameters and nuts and bolts of the system. But once we do, this simplicity happens. It just bear with us as system software writers. We'll get things right. It just may not be right fast enough. We'll work on it. So MPI-IO is under the hood of all these libraries. You maybe won't use it directly, but understanding what's happening will help you give you appreciation for the higher level libraries we'll talk about today. There's quite a bit going on, but if you want to learn more about MPI, there's an intro MPI man page on Theta and any other, and Cori and other Cray systems. I counted it. It's 2,900 lines, and every line is a tuning parameter of something you can do. It is overwhelming, and I love tuning I/O. So it's all there. You probably won't need to use many of those 3,000 lines, but there's lots of things you can do if you have a particular problem. And then this book, the Using Advanced MPI book, is a fantastic resource for talking about file views and the MPI consistency semantics. It's the book I used to learn MPI-IO when I first came to Argonne. It was purple back then, but it's the 3rd edition. It's fine. Again, even if you aren't going to use it directly, there's other good stuff in this book. So I would suggest, if it's not in your personal or work library, go ahead and pick it up. There's also RMA and other fun parts of MPI as well in there. So before we move on to parallel NetCDF, I'm happy to talk more about MPI-IO and transformations and the kind of library work that I do here.